This will be the first video talking about 5.1.1 spring mass systems, free undamped motion. In the exercises from 5.1, that's broken down into several types of applications, this being the first one with spring mass systems. All the problems that I'm going to be doing right now are in the engineering system with measurements of distance in feet, measurements of weight in pounds that we'll have to convert to slugs. Acceleration due to gravity is going to be 32 feet per second squared, and time is going to be measured in seconds. So just be ready for some of those conversions that we're going to make. There are other problems that are in the section that are in the metric system with your distances measured in meters, your mass measured in kilograms that you'll maybe have to turn into a weight that's in newtons, and time measured in seconds. So let's go ahead and let's look at our first problem here. It says a mass weighing 4 pounds. So my weight is mg is 4 pounds. LBS is the abbreviation for pounds. So my M is going to be 4 over 32 slugs is going to be 1/8 of a slug. Is attached to a spring whose spring constant, that's going to be K, is equal to 16 pounds per foot. What is the period of simple harmonic motion? So we need to use our equation that K over M is equal to omega squared. So 16 over 1/8 is equal to 128 is equal to omega squared. I'm terrible at drawing omegas. Sorry, but omega squared. And then that means omega is the square root of 128 is 8√2. And so my formula for the period, capital T, is 2 pi over omega. And so this is going to be 2 pi over 8√2 is going to be pi over 4√2. And we'll rationalize that by multiplying by √2 over √2. And we have √2 over 8 pi for our answer. All right, let's look at our next problem. Got plenty of space here to work it. A mass weighing 24 pounds. Is attached to the end of a spring and stretches at 4 inches. So I'm going to use the letter S to be the distance that it's stretched, 4 inches, but we need to measure our distances in feet. So that's 1/3 of a foot. Initially, the mass is released from rest. So x prime of 0 is equal to 0. From a point 3 inches above equilibrium. So x of 0 is equal to a -3. If it's above equilibrium, that's negative. If it's below equilibrium, that's positive, because positive is going to be moving in the direction of gravity. It's going to be pulling it down, so that's positive. And negative is going to be against that direction that gravity is pulling. So now we have mg let's just write that equation down for you. Mg is equal to Ks. We're going to be using that quite a bit here. So 24 is equal to K times 1/3. So K equals 72. And then we have omega squared is equal to K over M is equal to 72 over M. I didn't figure it out here, but M is 24 over 32 is 3/4. It's over 3/4. That's 288 over 3. Should be omega squared is 9d6. Yep. So my equation now looks like this: d2x dt2 plus omega squared is 96x equals 0. Now this m that I'm about to use is like our substitution that we did before. It's not mass, it's just our m substitution. So minus 4√6i. So my equation here of motion is, I'll need a little bit more space, so I'm going to scroll up here, is going to be in the form of x of t is equal to c1 cosine of 4√6t plus c2 sine of 4√6t. This is omega squared. This is omega. Just so you know, you can go straight to this form once you know what omega is. You don't have to go through this form with the m substitution every time. Let's see here. So also we need to know that x prime of t here is going to be a negative 4√6 c1 sine of, let's make sure that's clear, that's c1, 4√6t plus 4√6 c2 cosine of 4√6t. And so x of 0 was going to be -3. So that's going to be c1 cosine of 0 plus c2 sine of 0 is c1 plus 0 is c1, which is equal to a -3. And x prime of 0 is equal to -4√6 c1 sine of 0 plus 4√6 c2 cosine of 0 is 0 plus 4√6. This needs to be equal to 0. C2 equals 0. So C2 equals 0. And that means that my equation is going to be x of t is equal to C1 is -3 cosine of 4 root 6t, and then plus 0. So there's my equation. What did I do wrong here? I'm sorry, this is not -3. This is -3 was in inches. So my fault. This is -3 inches is -3 over 12 is -1/4. So this is -1/4, and that is -1/4. Always remember to convert your inches to feet. All right, let's go ahead and clear that. A mass weighing 20 pounds. This is number 5. Stretches a spring 6 inches, so that is 1/2 foot. Mass initially released from rest. Prime of 0 equals 0 feet per second. 0.6 inches below equilibrium. 0 equals 6 inches equals 1/2 foot. Okay. And this is a multi-part question. So I'm going to tell you that I know I need to find mg equals ks at some point. So 20 equals k times 1/2. So k equals 40. And that's going to be pounds per foot. That's what k is. So part A, though, asks me to find the position x at particular times. So I'm going to need to find my position equation. So now I have omega squared is equal to k over s, k over m, excuse me, is m is 20 over 32 is divided by 4, that's 5 over 8. This is slugs. So 5 over 8. So this is 40 times 8 over 5. 5 goes into 48 times. Omega squared is 64. Omega is equal to 8 here. So my x of t is equal to C1 cosine of 8t plus C2 sine of 8t. My x prime, which I'll need for part B, x prime of t is equal to a negative 8 C1. Actually, let's do all this right now so I can get the constant coefficients. Negative 8 C1 sine of 8t plus 8 C2 cosine of 8t. So x of 0 is C1 is equal to x of 0 is 1/2. X prime of 0 is going to be 8 C2 is equal to 0. C2 is 0. So my x of t that I'm going to need for part A is 1/2 cosine of 8t. And then on part A, we're asked to find x of pi over 12, which is 1/2 cosine of, when I multiply that, that's 2 pi over 3, which is half of -1/2 is -1/4. X of pi over 8, which is 1/2 cosine of pi. When I multiply that out, it's 1/2 of 1/2 times -1 is -1/2. These are all in feet because they're position. X of pi over 6 is 1/2 cosine of 4 pi over 3, which is 1/2 of -1/2 is -1/4 again. Same position, just coming from the opposite direction. X pi over 4 is equal to 1/2 cosine of 2 pi. 1/2 times 1 is 1/2 foot. And then remember, anything that's negative is above equilibrium. Everything that's positive is below equilibrium. And then we have x of, last one is 9 pi over 32 is equal to 1/2 cosine of, and that multiplies out to be 9 pi over 4 is equal to 1/2 times √2 over 2 is √2 over 4 feet. Okay, so that was part A. Let's move on to part B that says what is the velocity of the mass at the time t equals 3 pi over 16 seconds. So B is x prime of 3 pi over 16 is equal to, now this is -4. Let me find x prime of t here. This is -4 sine of 8t. So x prime of 3 pi over 16 is a -4 sine of 3 pi over 2 is a -4 times a -1. It's a +4. That's in feet per second. And this is positive, so this is moving downward. Let's look at part C here. And it asks at what time does the mass pass through equilibrium position? Equilibrium position is where x of t equals 0. So find t when x of t equals 0. And so we're going to have 1/2 cosine of 8t equals 0. So that means cosine of 8t equals 0. And 8t is going to be equal to our cosine of 0. To get all the answers for cosine is 0, that's going to be odd multiples of pi over 2. So that is 2n plus 1 over 2 times pi. And we're going to divide by 8 here, so t is exactly equal to 2n plus 1 over 16 pi, where n is equal to 0, 1, 2, so on and so forth. I'm going to skip number 7 because it requires you to do number 6, and it's also in the metric system, and I just want to skip all that and stay in the engineering system right now for these because I want to stay consistent. So I'm going to go on to number 9. So a mass weighing 8 pounds. Is attached to a spring. When in motion, the spring mass system exhibits simple harmonic motion. So part A tells me to determine the equation of motion if the spring constant is 1 pound per foot and the mass is initially released from a point 6 inches below equilibrium with a downward velocity of 3/2 feet per second. Okay, so that in mind, let's go ahead and find the equation of motion here, where mg is equal to ks. Actually, I don't need that. I just need omega squared is equal to k over m. So omega is equal to 2. So that means that x of t is equal to c1 cosine of 2t plus c2 sine of 2t, and x prime of t is equal to negative 2c1 sine of 2t plus 2c2 cosine of 2t. X of 0 is equal to c1 is equal to 1/2. X prime of 0 is equal to 2c2 is equal to 3/2. So c2 is 3/4, making x of t equal to 1/2 cosine of 2t plus 3/4 sine of 2t. This is the first time that we've seen something where we have both sine and cosine playing a role in here. So we are going to want to convert this into something that is in terms of all sines or all cosines to help us out later, and that's what part B and C say. So B wants us to write this in the form of Capital A is going to be my amplitude. So we want x of t is equal to capital A sine of omega t plus phi, where in this case, A is equal to the square root of C1 squared plus C2 squared. A is going to be square root of 1/2 squared plus 3/4 squared. A is square root of 1/4 plus 9/16. Multiply by 4/4 to make a common denominator. That's going to put me over 4. Square root of 16 is 4. That's going to be 4 plus 9 is 13 inside of a root sign. So that's root 13 over 4. That's feet here. And we want to find tan of phi is going to be equal to C1 over C2 is going to be 1/2 over 3/4 is 2/3. So phi is going to be arctangent of 2/3. Be careful about what quadrant you think you're in, because arctangent, you could be off by 180 degrees or pi radians here. I get 0.588 radians, which is in my first quadrant, which is where I want it to be, because both C1 and C2 were positive. So that tells me that I'm ready to write my equation. X of t is equal to root 13 over 4 times the sine of 2t plus 0.588, like so. And then part C asks us to do that, but for the cosine function instead. So my A doesn't change, but what does change is I need to flip this C1 and C2 here so that I get my tangent phi is equal to C2 over C1 is equal to 3/2. So when I take the arctangent of that, I get 0.983. And again, this is the difference here. This is going to be subtraction, and that's correct. I'm in quadrant 1 there. So x of t is going to be equal to root 13 over 4. And this is going to be cosine of omega t, but it's going to be minus phi. And the phi here is 0.983. All right, so we're going to need to rewrite some things going forward like that so that we can find times where this derivative is 0 and that we don't have two different parts in play. Change everything into sine or cosine so you have one function to take the derivative of. Let's go ahead and let's number 11. Number 11 has lots of parts to it. So just bear with me. I know that's going to make this video kind of long, but this will be our last problem for this video. A mass weighing 64 pounds. That means M is 2 slugs. Stretches a spring 0.32 feet. So mg is equal to Ks. So 6,400 over 32 is K, and 200 is equal to K. Omega squared is K over M is 200 over 2 is 100, meaning omega is 10. And we have x of t is c1 cosine of 10t plus c2 sine of 10t. X prime of t is equal to negative 10 c1 sine of 10t plus 10 c2 cosine of 10t. And what were our initial conditions? Mass is initially released from a point 8 inches above equilibrium. So x of 0 is equal to negative 8 over 12 is 3/4. I'm sorry, negative 2/3 of a foot. Yeah, 8 over 12. 4 goes into there twice and into there 3 times. So x prime of 0, downward velocity of 5 feet per second. So I don't need to change that because it's already in feet per second. Okay, so x of 0 is equal to c1 is going to be negative 2/3. X prime of 0 is going to be 10 c2 is going to be equal to 5. And so c2 is going to be 1/2. So x of t for part A. This is one of the ways in which we want to write the equation. We'll have to write it a different way later, but for right now, it suffices to write this as c1 cosine of omega t plus c2 sine of omega t. We'll come back and we'll write it in another way in just a little bit, because we won't want to have both sine and cosine going on when we are finding derivatives here. So we want to find the amplitude and period. So amplitude is going to be square root of negative 2/3 squared plus 1/2 squared is square root of 4/9 plus 1/4. So multiply by 4 over 4 and 9 over 9 is going to give me square root of 16 plus 9 over 36. It's going to give me an amplitude of 5/6, and that's in feet. Our period is going to be 2 pi over omega. It's going to be 2 pi over 10 is pi over 5. And this is, that's sufficient to just write it like that with no units. Let's look at part C now, which asks us to how many complete cycles will the mass have completed at the end of 3 pi seconds. So my frequency is the reciprocal of my period is 5 over pi cycles per second. And so I want 5 over pi cycles per second times 3 pi seconds. Seconds will cancel, pi will cancel. 5 times 3 is 15 cycles. At what time does the mass pass through the equilibrium position, heading downward for the second time? Okay, so this one's a little kind of crazy, but let's take a look at the problem. So the problem says that we start off above equilibrium and we start off downward. So our first time that we get a zero is going to be passing through the equilibrium, going downward. So that's n equals 0 is going to be, for our answer that we're going to get is going to be downward. And then we're going to be coming back upward. N equals 1 is going to be upward. And then n equals 2 is going to be downward again for the second time. So I'm going to want when n equals 2 here for part D. So let's find the, I'm going to want to change this though to the other form to be able to answer it easier. So I'm going to start off and write this as x of t is equal to a sine of omega t plus phi. Before I go any further, I haven't found phi yet, so let's go ahead and find that tan of phi is equal to negative 2/3 over 1/2 is equal to a negative 4/3. Tangent is negative in quadrants 2 and 4. I have this is in quadrant quadrant 4, I believe. Yes. So I'm going to come up with the correct and you draw your triangle so that it's C1 is in the vertical and C2 is in the horizontal. So this is like so. This is how we know that this was negative 2/3 and this is 1/2. So anyways, let's go ahead and go in here. This is x of t is equal to a, we already found was 5/6. Sine of omega we know is 10. T, and if I find arctangent of negative 4/3, I get that phi is just about a negative 0.927. So this was a plus, but it's plus a negative, like that. And so this is going to turn into 5. I want to find where this is 0, where it crosses equilibrium. So that's sine of 10t minus 0.927 equals 0, meaning sine of 10t minus 0.927 equals 0. And that's going to be 10t minus 0.927 equals arcsine of 0. That's going to be n pi. So 10t is n pi plus 0.927. So t is n pi plus 0.927 over 10. And when n equals 2, which is what we talked about before, t n, so I'll say t2 is equal to 2 pi plus 0.927 over 10 is approximately 0.721 seconds. And let's see, does it ask me? Doesn't ask me what the velocity is, but I'll tell you that the velocity here, x prime of t2, is going to be equal to 8 1/3 feet per second. It's going to be heading downward. That's why it's positive. So going here. Part E asks me at what time does the mass obtain extreme displacements on either side of the equilibrium position. So that's going to be when the first derivative is equal to 0. So using this equation here, x prime of t is going to be equal to 10 times that is going to give me 50 over 6 is 25 over 3 cosine of 10t minus 0.927 for my derivative. I want to take that and set that equal to 0. And solve it. And that's going to be cosine of 10t minus 0.927 is equal to 0. So 10t minus 0.927 is equal to, now this is going to be cosine is 0 at odd multiples of pi over 2. So 2n plus 1 over 2 times pi. So that's going to get me 10t is equal to 2n plus 1 over 2 pi plus 0.927, and t is equal to 2n plus 1 over 20 pi plus 0.0927. So that's my exact answer for part E. Question F asks me what is the position of the mass when t is equal to 3 seconds. So that's going to be negative. The most exact form is going to be this. Cosine of 3 times 10 is 30 radians here, plus 1/2 of sine of 30 radians, and type that into your calculator, and you're going to get negative 0.597 feet. Now, if you had used the other form with sine, you'd still get about the same answer here. It would be off possibly a little bit. G is going to ask me what's the instantaneous velocity. You'll definitely get a slightly different answer here. So again, most exact answer here is to use the derivative function here, and that's going to be 20 over 3 sine of 30 plus 5 cosine of 30, using that part that has sine and cosine in it. No problem sticking that into your calculator, and we get that it's about negative 5.816 feet per second. If we had used that other form, that is just the cosine function, we would have gotten about negative 5.814 feet per second. So go for the most exact answer that you can get. Since you're using a calculator anyways, don't use a rounded answer for phi on the inside and then round again. You'll see you'll get some rounding error. Just go ahead and stick in your angle and radians there and get your most exact answer that you can get. We won't really have a choice moving forward, though. We'll have to use those. So what is the acceleration at t equals 3 seconds? So I'm going to find the second derivative here of my equation. It's going to be 200 over 3 cosine of 10t minus 50 sine of 10t, and I'm going to go ahead and stick my 3 seconds in there. So it's 200 over 3 cosine of 30 minus 50 sine of 30. So x double prime of 3 is just about 59.685 feet per second squared. But if you had used the one that was just a sine function, you would have gotten the x double prime of 3 was just about 59.702 feet per second squared. So you see that each time that you take a derivative and you're multiplying there, you're getting a little bit more off each time. That this is your most exact answer, and we're getting off by a couple, by like 15 thousandths here now, as before we were off by 2 thousandths here for x prime, and we were right on for x. So again, just be careful with those functions where you approximate phi. All right, part I. No, it just keeps going, doesn't it? So what is the instantaneous velocity at times when the mass passes through the equilibrium point? So I asked us to find x prime of t when x of t equals 0. We're going to have two options here. And I already kind of told you that up here, that I told you that this is plus or minus 8 1/3 feet per second, because I already told you what the velocity was at one of those places. But let's go ahead and let's actually find that. That if I have x prime of, and I know that my I cross equilibrium at n pi plus 0.927 over 10. So that's going to be equal to 25 over 3 cosine of 10 times n pi plus 0.927 over 10 minus 0.927. This is my equation for my derivative here. So the 10s will cancel. It gives me 25 over 3 cosine of n pi plus 0.927 minus 0.927. Those cancel. 25 over 3 cosine of n pi. Remember, n is an element of the whole numbers here. So it's either even or odd. That's going to be equal to, if n is an even number, cosine here is going to be 1. And I get 25 over 3. N is 0, 2, 4, dot, dot, dot. I get negative 25 over 3 when n is equal to 1, 3, 5, so on and so forth. So this was part I. And let's keep going here. Part J asks me, at what time is the mass 5 inches below equilibrium? So find T such that x of t is equal to 5 inches below equilibrium. So that's 5 over 12. So we're just going to go ahead and use this sine function one because that's the only way to isolate the time easily. 5, 6 sine of ten t minus 0.927 is equal to 5 over 12. And then that means that sine of 10t minus 0.927 is going to be equal to 1/2. So that gives us two options, that 10t minus 0.927 is equal to pi over 6 plus 2n pi, or 10t minus 0.927 is equal to 5 pi over 6 plus 2n pi. And can go ahead and solve that. So 10t equals pi over 6 plus 0.927 plus 2n pi, or 10t equals 5 pi over 6 plus 0.927 plus 2n pi. So t is going to be equal to pi over 60 plus 0.0927 plus n pi over 5 exactly, or t is equal to 5 pi over 60 plus 0.0927 plus n pi over 5 exactly. So this t here is about 0.1451 plus n pi over 5, with n equals 0, 1, 2, dot, dot, dot. And this t is about 0.3545 plus n pi over 5, with n being equal to 0, 1, 2, dot, dot, dot. And The last question here asks us which of these pieces here is it heading upward? So you can do the work to figure that out, but this piece is downward, and this piece here is upward. So you can go ahead and you can stick one of those into X prime and figure out whether it's a positive or a negative value. And so this one is going to be X prime of t is greater than 0. And this one here is X prime of t is going to be less than 0 is how I'm going to know that. Just pick any value there on the cycle, because it should have the same velocity as it keeps coming back to the same place, since we're not losing any energy. All right, that's it for this video. I know this was a really long video. This is just the first set of problems in this section. I will come back and do some more spring problems in the next video, but this covers the first set of problems that I wanted to do. So see you for the next video.